Okay, good morning everyone. Welcome back from vacation. Today I want to start looking into the model-driven software design, model-driven software engineering aspect. So we switch context. We start looking into the methodology that we will use for developing algorithms and generating the corresponding software. First, before going into the lecture, let me just give you an update about the practical parts of the course. You have seen, I think, a message on Portata Didattica about the availability of LabVIEW software. You can get to the web link there, download everything and install on the computer. That is the material that will be needed for using MyRio boards. The second announcement is about the evaluation boards. I have received a list of vouchers for a 50% discount on procuring the board. NXP made a wrong click when generating the voucher, so the board is discounted, but you have to pay for the delivery. So I'm waiting them to update the vouchers. So we will have a 50% discount and free delivery, okay? That's why there is a delay. I noticed this problem, I notified that to Freescale. I'm waiting them for generating the new vouchers. I think it will take 1 day, and so I hope to be able to post by today the list of vouchers. Due to the fact that I have only 150 vouchers, I will assign 1 voucher to the students enrolled in this class for the first time. So each new student this year will have 1 voucher. Then I will show you the procedure, how to redeem the voucher, how to buy it. The board will be bought directly on NXP website, so it will be delivered from US. Normally it is fast delivery and the amount is very low, so I don't expect that there will be import fees, okay? But I will let you know as soon as possible about the procedure for procuring the boards. That's it, so let's start with the lecture. Today I want to analyze the introduction of this chapter, as well as some concepts that will guide us in using this concept during the practical phases that we will face. Let me start first thinking about a model. So why do we need a model? That's the big question that we have to answer today. In order to give an answer to this question, let's think about what a model is. A model is an abstraction or a simplification of the reality. We have a very complex item in mind. We have to attack the design or the analysis or the evaluation of that item, but the item is full of details, so many that we can't handle all of them at the same time. So we need to find a way for making the problem simple, so that being simpler, it is attackable. If it is not possible to simplify the problem, we will not be able to solve it. So this simplification process exploits one of the capabilities of our mind, that is the abstraction. The abstraction is a mix of 3 components, I would say. We have the capability of generalization. This means that we are able to look into an object to extract specific features that are those relevant for what we want to do, while keeping all the other features that are not relevant on the background. Then, based on this generalization, we are able to classify. So if we see other objects that are different from the one that we analyzed first, but that contains the same relevant features, we are able to group them together in the same class. And then, thanks to the capability of generalization and classification, we are able to put together objects that could fit together through the process that is known as aggregation. So these are all the concepts that we exploit in order to start from a very complex problem and simplify it to the point where the problem is manageable. What we obtain is a partial representation of a physical object, of a physical system, that conveys only the relevant properties, the relevant features for which we want to make some analysis. This discussion seems quite impalpable, very abstract. Let's try to put this into an example. So let me show you an example that is intended for clarifying the concept of model. Let's take this picture. This is a picture of a ball. Let's imagine that this is our original system. As you can see here, we have a very detailed picture, although the resolution is not very nice. But anyway, we can see all the different elements of the ball. We can see the big body, we can see the horn, we can see the muscles that are distributed in the body, we can see the tail, the legs. But this is very, very, very detailed image of the physical system that we are analyzing. There is a lot of detail here that probably is not necessary to describe a ball. If we want to describe a ball, the relevant features that we have to take into account are the four legs, the tail, the two horns, and the big body. Then all the different shades of colors that we have in this picture are not relevant. They are adding details, but they are not changing our association of this shape with a ball. So if we want to build a model that abstracts all the details and that is still able to convey the information about the ball, we have to throw away details till we just have the relevant features. And this is the creative process that Pablo Picasso used for building this sketch. This is the representation of the ball. It is a famous drawing of Picasso, where you can see all the relevant features of the ball. We have the big body, we have the four legs, the tail, the horns. So here we can say that we have a model. If you compare the two pictures, it is clear that here on the model we have very little detail compared to the full system, to the original system that is depicted in this picture. But anyway, the set of features that we kept on this drawing is very limited compared to the original system, but it is enough for the purpose of this image. If you want to convey the image of the ball, this is enough. We don't need to have all these details, okay? This is just an example. What we want to do starting from now is trying to understand which is the process that we can exploit in order to model software in such a way that we focus on what is relevant. So the functionality of the software or the properties of the software that we want to express. Then all the details, while we keep them on the background, somebody will take care of that. They are not relevant for the moment, okay? So we said that the model is an abstraction of the reality. Then, as a result of this, we say that the model contains only some features of the overall system. So you may wonder whether the same system will lead always to the same model. Well, the answer is obviously no. Depending on what we want to achieve from the model, starting from the same original system, we will build different models capturing different properties that are relevant for the specific activity that we want to do. Let me give you an example. Let's imagine that we want to design a control system. We are designing an automatic system for controlling the suspension of a vehicle. These are active suspensions, so they have to adapt the stiffness and the damping to the shape of the road where we are traveling. So let's imagine that we have to design this system. So if we want to design with this system using a model, we cannot start modeling all the shapes of the vehicle where the suspension system will be integrated. It is too detailed. You have to throw away something. You cannot represent all the different elements of the vehicle just for obtaining a representation of the vehicle that we can use for deriving the control. We need to throw away something. We don't care about the color of the vehicle. In first order of approximation, we don't care about the shape. What is relevant is the mass of the vehicle. It is relevant to know the type of shock absorber that we are using, okay? Which is the characteristic of the dampers that we will control in order to implement the active suspension system. We need to know the characteristics of the sensors that are attached on the body of the vehicle and on the spring in order to provide the inputs to the control system so that we are able to design the control system. But we don't need to have all the details. Then let's imagine that we want to build a model that is intended for studying the consumption of that vehicle when moving in a certain road condition. Well, in this totally different scenario, starting from the same physical object, the vehicle, it is very likely that we will build a totally different model. In this second example, we need to know which is the shape of the vehicle, because thanks to this knowledge, we will be able to compute which is the force that is applied by the wind on the vehicle when it is moving at different speeds. And this obviously will contribute to the computation of the consumption of the vehicle. The vehicle is always the same, but the purposes are different. In the first case, we want to design active suspension. So we will look only to few features of the vehicle. And we keep aside the shape. We don't care about the shape. The second example, we want to estimate consumption. Well, in this case, the shape is relevant because it is something that is facing the air, that is producing friction, and so it will contribute to slowing down the vehicle so that if we want to keep a certain speed, we need to accelerate, and so we will increase the consumption. So this is schematized on this slide for what concerns the software, given the system we want to design, that it will be an embedded computer with hardware and software. We may build different models here. So we can do models intended for static analysis. Let's say the model that is intended for representing the different execution paths of the software so that we are able to perform validation of the code inspection all those techniques that we have mentioned when talking about ISO 26262. Another example, well, it's a model intended for documentation. Let's imagine that our model is, our software is made of multiple functions that interacts in some way, for which we have a number of data objects that are exchanged, and so on and so forth. If we want to represent this concept, we may want to use a model that gives us the structure of the code. We don't care about what is inside every function. We just need to know how many functions we have and how they communicate each other. If we do rapid prototyping, well, we need to have a model that conveys most likely the functionality that the system has to provide, so that we are able to run this on rapid prototyping hardware. We will see this later on. Similarly, if we want to obtain source code starting from the model, well, we will have to think about which are the features that we have to convey in this model so that it can be used for representing software. So, as you can see, starting from the same object, we can build many different models that serves many different purposes. In this class, we will look into, for sure, code generation and rapid prototyping, and we will look a little bit also into documentation through suitable techniques intended for deriving suitable models. Then, now that we understood more or less what a model is, the question is, why do we care about model engineering? If you are used to do programming in a certain way, you are very skilled in C programming or whatever, why do you want to change the approach to design software? Well, this is, the answer can be found in the complexity of the software. Today, we have to deal with very complex systems. Think about the active suspension system. That is something not trivial at all. You cannot start conceiving such a kind of system without an understanding of the physical phenomena that are going to be controlled, and without having an approach that allows you to reason on the algorithm well before you start writing a single line of C code. So the answer for why model engineering is worth is due to the complexity of the software. The things that we have to do are too complex. We cannot afford the design of such a complex system unless we have some abstraction techniques that allows to build a model that simplifies the entire design process. Then, as a result of the complexity, we have some unpleasant side effects related to the software development. One of these problems is that the software are finished too late. Remember that when you enter a company, you will have to do your job on time. There will be scheduling for the project. This means that you will be assigned a task that has to be completed by a certain deadline. And then, based on that, a new task will happen, or somebody else will start doing his or her own activity. So, if you have a delay, then this will impact potentially very heavily the entire development of your product. So, if the software is complex, it is difficult to implement it, it is difficult to have it working correctly, and this is a big potential for delays. And this is something that we want to avoid. Delays can come both from the complexity that is intrinsic with writing the software that somebody is asking to you, but also due to the difficulties of debugging your code. you have tried to program for sure. So you know that once you start writing your code, you start putting bugs in your code. The more complex is the software, the higher is the number of bugs, the longer it takes to remove all of them, if it is possible, from your code. So when you deal with complex software development, dealing with bugs can be a very painstaking problem that will take a lot of time to complete. And this, again, is a possibility for delays. Let me give you an example. This is the number of bugs per 1,000 lines of code, LOC stands for lines of code, that was found in 1977. It is about 20 bugs every 1,000 lines. Then somebody took the time to make an analysis on the code of 1994, so plenty of years ago. They found that the number of bugs per lines of code was reduced to 0.2. So at the first sight, this could be very, let me say, encouraging. Oh, the number of bugs is reduced hundreds of times due to the new techniques of traditional programming. Well, the downside of this story is the fact that the number of lines of code in a software is increased significantly from to 10,000 lines of code in 77 to 800,000 lines of code in 1994. So you can see here that the number of bugs in terms of absolute count that you have is nearly the same. So even if, starting from 77 to 1994, we have seen a significant improvement in the way in which software is written, let's say instead of writing software in assembly code, as it was happening in 77, we now use C code. So it's a very powerful advantage here, so that we don't have to deal with opcodes and movements of data between registers, but we can use in very complex statements like if, then else, for, functions, whatever. The number of bugs in our product remains nearly the same. This means that if we project this data today, we are still the same troubles. We have code with tens of millions of lines of code, and so we have thousands of bugs. And if we want to deliver our product on time, we have to fight against them. If you look at recent examples of big development projects, you can see that you have something like one architect, 10 developers, 50 debuggers. So 50 persons that are there to test the software, find bugs, and then issue bug reports to the developers. This is because the software is becoming bigger and bigger, and the number of bugs is becoming higher and higher. So it is not possible to go ahead like this. And if you have to attack projects where you have also time as an element of the design space, like it happens with automatic controls, then the problem is becoming even more bigger. So using the traditional approach, we cannot continue to design systems as complex as the one that are requested today by the market. We have to change the paradigm. And this changing is model-based design. This is something that is already a reality. If you look into what GM is doing, so the door next to us, they are using code generation, they are using model engineering very heavily. So the powertrain is not controlled by C code handwritten. It is controlled by an algorithm that is designed starting from Simulink, and the code is automatically generated. If you look into what FCA is doing, it's the same. If you look at the big companies in Germany working with automotive, well, they are all using model-based design for real-time control. So this is something here to stay, and you will have to face it if you enter an industry designing some form of control. As mechatronics students, it's very likely that this will happen. So it is important that you understand this concept. So model engineering, as we have seen a couple of slides ago, is based on models for a number of purposes. That is documentation, code visualization, definition of the structure of the classes of software, and so on and so forth. But why model-driven software engineering is different? Well, the answer is here. The process that we will follow is the following. So we will use models as draft. This is a way to say that we will use the model as the worksheet with which we conceive our algorithm. We will use the model as a way for expressing the different ideas that we have, sorry, for evaluating the different design alternatives and for communicating with your colleagues. If one of you makes a model and then the other one takes the same model, based on the knowledge of the modeling language, you can understand each other. So you can discuss, you can collaborate. Then the model is also a guideline. When we have the model set, that is the reference. The model says what we want to do. And that is our reference. Our design will have to reflect what the model says. So the model is the specification, is the goal we want to achieve in the implementation phase. But then, what is also important is that the model will serve also as a program. Thanks to the technique that we will learn, we will be able to derive automatically programs starting from the model. So this is a big advantage because you don't have bugs. You are not writing any line of code, in principle. So you can't forget a parenthesis, an ampersand, or an equal in a certain statement, so that your code will intrinsically be better. So this is what we want to achieve. And well, this is not new. There are already many examples of industries that are using this concept. Give you an example. Think about Airbus. Airbus is a big company building a lot of things. One of these is airplanes, like A340. This is an intercontinental plane. But if you ever had the chance of taking an Airbus 319 or 321, this is the typical planes that are used within Europe, well, you have flown on Airbus product. Well, if you look into the software that is deployed on these planes, you will see that about 70% of fly-by-wire controls are model-driven. So this means that somebody in Airbus designed the model of the control algorithm that keeps the plane in flight. And then this is done with a specific tool. We don't care about that. And then the code is generated automatically out of that. So 70%. This is not negligible. If we look into another example of application is a Eurocopter. This is making helicopters. 90% of the autopilot is model-based. Let's see PSA. PSA is Peugeot Citroën. So this is a company dealing with automotive. Well, 50% of the electrical management system of the vehicle is totally model-driven. So they generate the model and then they automatically generate the code out of the model. And which are the advantages that have been observed by adopting this? Well, if we think about Airbus, we have 20 times reduction in errors. So 20 times less errors. This is a huge amount of time. Reduction of time to market. Eurocopter, 50% reduction in cycle time. So the time it takes to design a new software release is divided by half. About PSA, 60% reduction in cycle time, 5 times less errors. Well, 5 times less, 20 times less can seem just impalpable figures to you. But you have to imagine that for each error, you have somebody that has to spend time sorting out the source of the error, finding a test case that highlights the occurrence of the error, and then somebody else has to take care of investigating the code and fixing the error. Okay? So this means time. It could be 1 hour, it could be 1 day, depends on the error, for identifying the error, and then time, 1 day, 1 hour, 1 week, again, depends on the error, for fixing the error. So this is time that your company loses fighting against errors, and this is money that your company loses in fighting against errors. So if you have an approach that by construction gives you a factor of 20 in the reduction of errors, well, this is a big cost saver. So even if putting at work model-driven engineering is expensive, as you will see in a minute, the saving that you have is very significant. Okay, now let's move to the concepts. So we have seen what a model is, we have seen the purposes of models. Now let's go into the details of what we want to do. So the principles that are aiming our activity are the following. The first one is, well, we already faced this in the first half of the lecture, that is abstraction. So we want to have an instrument that is able to support us in specifying the relevant features of the system we are designing. So we need to have this kind of tool. Then we need to have an automated code generation. So we don't want to spend time in writing C code. Our environment must have a tool that is able to translate a model into a piece of code that we can run. And then we want to have a design flow that supports the separation of the development of the application and the computing infrastructure. We will clarify all these aspects throughout this lecture. First of all, let me show you the basic architecture that is supporting our considerations. So, our goal is to build an application. The application is conceived through a model. We have seen in the first half hour of this lecture that the model is the abstraction of the physical system that contains all the properties that are relevant for what we want to do. This model is obtained through a modeling language. This modeling language is specific for a given application domain. Do we want to design an application that is a control system? Is the control system a time-dependent system? Well, we will use a language that is able to specify the properties that are relevant of our control system in such a way that it is simple for us to express those properties. And maybe we can also have the capability of simulating what we are specifying so that we are able to test whether the algorithm that we are designing is doing what we are expecting, and we are able to compare different alternatives. The language that we are using is not specific of a certain computing architecture. This is generic. Think about Simulink. When you have a Simulink, you can draw a schematic that represents an algorithm, like, for example, a control algorithm. You may have seen already some part of Simulink. You know that you have blocks, each block with a specific meaning. Then you can interconnect these blocks to assemble a more complex behavior. Well, one of these blocks is the integrator, 1 over S, okay? That is clearly a mathematical function that we can use for transforming an input signal. Let's say we have an acceleration that is arriving from a certain sensor. We want to compute the velocity, so we integrate the acceleration, okay? So this is part of a control algorithm. This is something that allows us to express in a nice way the control algorithm using terms that we have seen from control theory. Then, when we do this activity, we don't care how the integrator will be implemented. Is this an analog circuit that does the integration through operational amplifier? Is this a digital system that does the integration through a program running on an embedded computer? We don't care. Now we are designing the model of the control algorithm. We know that in the control algorithm we need an integrator, and that's it. We use the integrator function. We don't care about how this is implemented. So the modeling language that we are using is specific of the application domain we have to target. We have to design a control system that is based on a state machine so that we have different operational states that are reachable according to the specific set of input sequences that are provided. Well, if we have to model that, it is very likely that the traditional Simulink approach that you know is not fit. We need to use something different. For example, we can use Stateflow, that is an add-on of Simulink that allows to design state machines. And this is something that we will do in this class. Then, let's imagine that we addressed our design here through the model. So, resorting to the modeling language that is fit for the application we have to deal with. And the modeling language is based on a set of constructs that defines the language, and this is the meta modeling language. We have built a model, and now we know that that model contains a reasonably accurate description of what our system shall do. Then, according to model-driven software engineering architecture, we can follow the path towards the bottom of the slide. So, starting from the model, we will apply transformation rules. These transformation rules are automated. So it is a kind of push button for the designer. Starting from the model, there will be a tool, the code generation tool, that will take care of transforming the model into something else. This is regulated by a set of transformation definition, and these are specific of the purpose we want to achieve in this transformation. Do we want to generate documentation? Then the model will be translated into a Word document with all the needed information to document your design. Do we want to generate software code? Then the transformation rules will take care of taking all the Simulink blocks and translate them into a piece of code, a piece of C code, and then glue together properly this code to have a set of C functions whose behavior is exactly the same of the Simulink model. Okay? This is done through a suitable tool, the code generation tool, that exploiting transformation definition translates the model into an artifact. For example, a piece of code. Here we have to be platform aware. The platform is the definition of the infrastructure that will be used for executing the model. Think about the platform in terms of an embedded computer. The embedded computer contains a certain amount of memory. It has a certain clock frequency. It is able to provide a certain set of inputs and outputs. All of them are properties that defines the platform. Well, the model that we translate into code shall fit into that platform. So the code generation will produce an artifact that is based on the transformation rules, but it is also targeting a specific execution platform. Let me give you an example. Let's imagine that we have a Simulink schematic. We want to generate the code that has to be deployed on an embedded computer without an operating system. So the transformation tool, the code generator, will have to generate all the instructions that are needed for making that code resulting from the Simulink model able to execute on a platform that has no support from any operating system. So there will be a certain task. We will see this in practice. Other possibility, we want to generate code for an embedded computer that contains Linux. So it is very likely that in this second case, the artifact will be a set of Linux processes that encapsulate the C code corresponding to the model. The two codes are totally different. They are starting from the same model, but they are different. This is because the computing platforms that we adopted as example are different. Okay? So for the moment, it is important that you understand the process. We have the model that is specified through a suitable modeling language that is platform agnostic. So the model here doesn't know nothing about the platform. Let's say our system is a control system that is based on two inputs coming from the plant we are controlling and produces one output that is the command to be applied on the plant. While working on the model, we know about inputs and outputs that are, let's say, in-out ports in Simulink. They are just wires that bring something inside the subsystem that models the controller or that brings the output of the controller outside. And that's it. You attach a stimuli on the Simulink schematic, you attach a probe on the Simulink schematic, and then you see what is happening. Okay? Then, when you move towards the platform, well, the two inputs shall become something corresponding to physical sensor. Let's say we have an acquisition chain that is controlled through suitable firmware that provides data that are the measurements on which the algorithm has to deal with. Well, when working at the model level, we don't care about how data are produced and how they are used. We just care about the transformation of the inputs into outputs. When we generate the code and we plug this into an execution platform, well, we need to add more details. In particular, we have to know where the data comes from and where the output has to be produced and applied to the system. For the moment, it is very abstract, all of this. We will put this at work so we have an understanding of this concept. Now, before a short break, because it seems to me that they are pretty exhausted, let me have a few words about the type of models. We have seen that depending on what we want to achieve, we could have different models. Roughly speaking, we can find two broad categories. The first one is the category of static models. The second one is the category of dynamic models. In the static models, you are interested into the architecture of the system. Think about the ISO 26262. We have seen that we start from the system design, where we define the architecture of our system in terms of, let me say, big boxes that are some way interconnected. We don't care about what is inside the boxes. We just have to take decision about how we want to partition our functionality into sub-functionalities and how these sub-functionalities has to interact. This is a static model. We haven't yet assigned a behavior to each of the boxes. We are just considering how many boxes we have and how they interact. Think about the equal system. We have the needs of getting data from the CAN network, then we are getting data from sensors, then we do some computation, and then we issue the call because we recognize that there was an incident. Well, you can start imagining the architecture of the software there. We can have some block that are intended for interfacing with the sensors. Then we can have another block that is intended for interfacing with the CAN network. Then we can have another block that contains the application logic. So taking the inputs from the other blocks decides whether to make the call. And then we can have another block that is responsible for managing the modem to making calls. Well, here we have defined a set of elements of an architecture that are a set of blocks with a tag that is the purpose of the block. We can detail the interface of this model. Let's say we get the data from the accelerometer. We provide this after it has been filtered to the application logic block. We can reason about the different blocks, the different interconnection, but we haven't specified yet in a not ambiguous manner what each block has to do with a level of detail suitable for making, for example, a simulation of this architecture. So this is important when you want to define the architecture of your system, because there you decompose the system in simpler parts, and then you may decide whether you can buy some of this part out of the market, or if you can make some other parts of this architecture. But this is still a static model. Then you can have dynamic models where the emphasis is on the input-output relationship that the model has to provide. So these are models that you can simulate. These are models where you specify which are the rules, which are the laws, which are the algorithms that takes set of inputs and generates set of outputs. And while you do this modeling, you can make simulation. So you can analyze how the output of the system evolves over time. This is why these models are dynamic. These are models that you can simulate. The static models, you can't simulate them. There is no behavior specified there. There are just the interfaces. So what you can do there is static analysis. You can check whether the different blocks stays together nicely. Okay? Okay, so let's have a 10 minutes break, and then we resume lecture at 9:30.